So thanks, Randall and Alexander and all the organizers of the seminar series for giving me the opportunity to talk about this. So I'll start. So this was an event detected with CHIME, which is a telescope in British Columbia in Canada. It's a cylindrical telescope that's 100 meters long and 20 meters across, and it's built by a team of primarily Canadian universities, and then a few other American universities that we've accreted onto the CHIME FRB project. The four cylinders are oriented north-south, so the field of view that CHIME sees is a strip along the meridian in Penticton. And we instrument the focal line with 256 feeds on each cylinder. And so the total of 1024 feeds run underneath the telescope and get processed in a fairly beefy correlator in these two shipping containers here. And then we have an FRB search machine in this shipping container here. So all those feeds, why am I not? Oh, there we go. So the telescope feeds three different projects. So one is the Canadian Hydrogen Intensity Mapping Experiment itself, the namesake of CHIME, whose goal is to map the 21 centimeter hydrogen signal to probe the effects of dark energy on the expansion of the universe in the redshift range 0.8 to 2.5. And that redshift range is what sets the observing band of CHIME, which is 400 to 800 megahertz. And in that 400 to 800 megahertz band, we have a project to search the large field of view of CHIME for fast radio bursts, and another project to time galactic radio pulsars as they pass over CHIME daily. And for most pulsars, that project can get daily to almost as good as weekly cadence. But here we'll be talking about CHIME FRB, and so what a single cylinder sees is a field of view a few degrees wide that stretches from horizon to horizon. And what we do in the correlator is we form beams on the sky in 4 rows. And so we form 4 rows of 256 beams interferometrically, and then each of those beams we search for impulsive millisecond to second duration burst signals, which are fast radio bursts. And so if you don't know what fast radio bursts are, they are fast, meaning millisecond duration, bursts of radio waves that look like they're coming from far outside of our galaxy. And the reason that we think they're coming from outside of our galaxy is that they have a large dispersion measure, or DM. So as radio waves propagate through the interstellar and intergalactic medium, the plasma between us and the source delays the light as a function of frequency, and you get this characteristic dispersion sweep seen here. We measure that sweep and correct for it and sum it up to get the band summed pulse you see here in this panel. And the high dispersion measures of FRBs imply that they're coming from distances up to a redshift of 3. And so that, is a cosmological population. These extreme distances mean that they're quite intrinsically bright. FRB's sources span 10 to the 37 to 10 to the 42 ergs emitted. And their origin is currently a mystery, although as you'll see, the detection here maybe helps out with that mystery. We know of 126 published FRBs, some of which we have detected repetition from. And CHIME's work is the high field of view of CHIME is giving us several FRBs per day, and we're working towards a release of a catalog of hundreds of FRBs from our first year of operation, which hopefully you'll see sooner rather than later. But the event I'm talking about here is not an extragalactic fast radio burst. It is coming from a magnetar in our galaxy. So a magnetar is a pulsar, a neutron star, with an extremely high magnetic field. And that extremely high magnetic field, up to 10 to the 15 Gauss, powers high X-ray luminosity, which most FRBs, or not FRBs, magnetars, are detected in the X-ray and monitored in the X-ray. A few have been detected in the radio, but it's a small portion of the known magnetars. And the high magnetic field powers outbursts and flares, as well as rotational timing variations. If you're not up with magnetar jargon, an outburst is a prompt increase of persistent X-ray flux that's followed by a decay that can be up to many years, take many years to return to quiescence. And then a short X-ray burst is has durations of milliseconds to seconds, and these bursts are preferentially emitted during outbursts. And so magnetars are a favorite model for FRBs, even before the event that I'm going to tell you about shortly. Ever since the first repeating FRB was discovered in 2015, they've been a popular model because you have a short duration of FRBs implies a compact object origin, and the high magnetic field is a large reservoir for powering these energetic bursts that we detect, across the universe. And there's many theories on how to generate FRBs from that reservoir. It's a pretty active area of investigation. And so the source, the galactic magnetar that got us all excited, is SGR 1935 plus 2154. It was discovered in 2014 by the swift burst of the telescope, which triggered on some short X-ray bursts. And you can see in this figure here from a paper in 2017 that the number of bursts as a function of time over many years, and then the flux curves of the outbursts, that it has these outbursts quite frequently in 2014, 2015, and 2016, where it emitted several bursts at the onset of the outburst, and then there was some flux decay. And then in April 2020, it went into its most recent outburst, and here's an example from an ATEL from the nicer folks on detecting hundreds of bursts within 10 to 15 minute period here. So it's quite active in the X-ray on April 28th. And so on April 28th, we saw a burst that consisted of two peaks about a few milliseconds wide. And the dispersion measure that it was coming from, of 332 parsecs per cubic centimeter, is at its location is consistent with coming within our galaxy, and consistent with what is known about the distance of SGR 1935. SGR 1935 hadn't been detected in the radio before, and so we didn't have a dispersion measure measured for it, but it is consistent with the distance to that source. The spectral features you see here are not the event itself, but an artifact of how we detected the burst. So you have these features that are evenly spaced knots, and that's because of where we detected the burst. So SGR 1935, when it hit our telescope, was 22 degrees off the edge of the main field of view where we form our beams. And our beams are quite, the sensitivity of our beams when you get out into the side lobes is low, and it stretches that low level sensitivity stretches all the way up to the horizon, but it's very frequency dependent, and that frequency dependence is what leads to this knotted spectrum. And because we know how CHIME forms its beams, we can fit a model of that frequency dependence, and that's how we localize the FRB to put it, and found that it was at the location of the magnetar. That and the known activity of SGR 1935 gave us no doubt that this is coming from the magnetar. And so later that day, on April 28th, we threw out an ATEL to let everyone know that this exciting thing had happened and point your telescopes at it. And this event was quite bright, so it wasn't just detected in a telescope with 100 meters of collecting area. There's also the STARE-2 experiment, which stands for, and I hope I don't get this wrong, apologies to STARE-2 folks if I do, Survey for Transient Astronomical Radio Emission 2. I think I got that right. And they are feeds pointing straight up at the sky with no reflector to collect light. And so they have a very wide field of view on the sky, but not very much collecting area. And so they saw SGR 1935, the burst that we observed from SGR 1935, just the second peak here, where you can see our spectrum here. The spectrum of this component rises towards higher frequencies, so it's not a surprise that they, that's the component out of the two that they detected. And STARE-2 is several of these antennas across the western US, which allowed them to also localize it to the location of SGR 1935. And so their telescope independently detected it, and their RHL prompted them to quickly look at their data and say, hey, look, we saw it too. STARE-2 is much less sensitive than CHIME, so the fact that they saw it told us that this thing's definitely bright. Because of the side lobe location of where we detected the burst, it took us a bit to figure out exactly how sensitive our telescope was at that location and to figure out how bright this event was. But once we did that work for the paper that we've submitted to Nature, we found that it's around, if you put it for a fiducial distance of 10 megaparsecs, or not 10 megaparsecs, 10 kiloparsecs to the to SGR 1935. The energy that it would have put out in that burst is 10 to the 34 to 10 to the 35 ergs. And if you compare that to things that have been previously seen in our galaxy, like giant pulses from the Crab pulsar, and another event from the magnetar 1E1547, that's several, 4 to 5 orders of magnitude higher than what had ever been seen before, and only an order of magnitude or two below the energies of the faintest, most nearby FRBs that we've detected. Of course, it's still 8 or 9 orders of magnitude below the brightest FRB, so it's harder to connect this event to that end of the population, but it's certainly easy to connect it to the faint end of the FRB population. And to emphasize that, SGR 1935, the burst from SGR 1935, if you put it in some nearby galaxies, so our closest neighbor Andromeda, it would be detected at 300 Jansky milliseconds. So if you're not a radio FRB astronomer, for context, CHIME's on-axis detection threshold, so coming in our main field of view, is about of order 1 Jansky millisecond. And then if this event in 3 minutes, yeah. If this happened in a galaxy 10 megaparsecs away from us, so relatively close by, it would have been detected around that threshold. The closest nearby FRB to us that we have well localized, where we've found the host and so we know the distance, is at 150 megaparsecs. And so you'd have no chance of detecting an event like this in that galaxy with CHIME. So it's still not quite, as bright as the FRBs we see in other galaxies, but it's, if this event had happened in a nearby galaxy, we would have called it an extragalactic fast radio burst, right? In reaction to our ATEL, people looked at their data for high energy counterparts to the radio burst, and they found that there is a X-ray burst that happened at the time of the radio burst, and it has 2 peaks which line up with our radio components. And in terms of energetics, it's not exceptional. It's about middle of the range for magnetar X-ray bursts. But they found that its spectrum is harder than the other bursts from SGR 1935 and what the most X-ray bursts, magnetar X-ray bursts show. So it is exceptional in some ways, but certainly not energetic. So it's, in terms of energetics, it's odd that, you know, a vanilla X-ray burst had this incredibly bright radio burst, and then all these hundreds of other X-ray bursts, there's no radio emission from, detectable radio emission. So there's a little puzzle there. But a puzzle that I don't have time to get into. But to summarize, CHIME detected a millisecond duration radio burst, which you could certainly call fast, from SGR 1935, which is a galactic magnetaran outburst. And this is the first event that comes even close to the energetics of FRBs that we see in other galaxies. But we know the source of this one, which is a big difference. But it's whether or not we can connect this physically with FRBs is certainly tempting, but it's still an open question, and we'll have to do more observations of both magnetars in our galaxy and nearby FRBs to see, can this, you know, does this match up with what we see for all FRBs, for some, etc. Okay, thank you, everyone, for listening.
Thank you very much, Paul, for this great overview, all these observations of this very exciting event. So we have time for 1 or 2 questions. So let me look here. Maxim Lyutikov asks, can you comment on the relative timing of the radio and high energy bursts down to milliseconds?
I think, so I'd have to refer to the papers, but I think they're consistent to within a few milliseconds, so within about the width of the X-ray peaks here. So at least at this stage, to my knowledge, we can't, you know, constrain, for example, which component, radio or X-ray, came first. Certainly the rise of the X-ray here came first, but we're not sure, you know, the peak.
Okay, and then there's no other questions from the audience, so I'm going to allow myself one question here, which is for the 2 peaks in the radio, as you showed, they do show some different spectral behavior. What kind of constraints do you actually have on the spectrum, the spectral slopes, or how different they really are?
Yeah, so this is very heavily, you know, the frequency dependence of our telescope is quite complicated here, but it doesn't change on a time scale of 30 milliseconds. So this, you know, spectrum that rises towards the bottom of our band, and then this one that rises towards the top, is, you know, from the source and not our telescope. You see quite things like this in FRBs, where you have you know, spectra that are band limited within the 400 to 800 megahertz that CHIME has. So it's certainly, these extreme type of spectral variations aren't unprecedented in FRBs. So that's maybe another hint that this, you know, isn't crazy to connect these events together.
Okay, thank you. And there's actually a comment from Sandro here: with integral, we observe a delay of 6 milliseconds between the radio and X-rays, X-ray peaks, X-rays lagging. Okay,
so that would be, you know, an answer to Maxine's
question. Yep.
Yeah, I'm aware of that.
And I have a quick live question. You said that it's not energetically, that this burst was not energetically exciting in terms of X-ray emission, but is it, if you just look at the ratio of radio flux to X-ray flux, is this the largest we've ever seen? Do you have any way knowing how it compares in terms of, you know, LR over LX?
So comparing the, you know, taking the ratio of the energies is about 10 to the 5, you know, 5 or 6 orders of magnitude difference. So there's, you know, 5 to 6 orders of magnitude more energy in the X-ray detected than the radio. And I'm not sure that's when we can't really compare that to FRBs, because those energies would not be detectable at the extragalactic distances. And we've tried to put limits for FRBs on the X-ray and gamma ray fluence at the time of FRBs, and our limits are still several orders of magnitude above that level.
Okay, thank you very much, Paul. And Many thanks to all three speakers for these very nice talks in this first series.